Hi class, it's Bill Beck, continuing in our exploration of priority queues, heaps, and we'll get into heap sort at the end, but we're still on our heaps for the moment. And in the first video, or the previous video, we talked about the basic ideas behind heaps, that they are binary trees, but they are organized differently than a BST. Talked about the definition of what they are, min heaps, complete trees, max heaps, we got all that down. Now we want to start looking at how we make them so fast. Because remember, what we want here is add at log n and remove at log n. So how are we going to do that? Well, the properties of a heap are going to make that make sense. So let's look at what you do if you need to add a value. Well, the first thing we have to realize is we have to make sure that trees are always complete. So add, the first thing you have to do is add at the next available spot. So if we were going to add 15, this has to be the spot where it goes, right? It has to go at this spot right here that is marked in red, has to go there because that's the next available spot. That's how a complete tree is maintained. So the first thing is put it there. Next thing is check it against its parent. Now how we're going to know the parents and the children is an interesting thing, right? One of the problems with other kinds of trees is moving up is not so easy, right? With a binary search tree, there's no link to find the parent. So how are we going to do that? That's another thing to consider that we're going to talk about when we do implementation. But for the moment, just think about it conceptually. So we have to take the 15 and compare it to the 60, and since this is a min heap, if that's smaller, these two have to swap. So the 15 has to take the place here, and the 60 is going to move down here. So now we have the 15 here. Now we have to keep comparing to its parent. So we compare the 15 and the 20, and we see that those are out of order, so they need to be swapped. So the 15 comes here, and the 20 comes here. Now we have the 15 here, and we compare it to its parent, and the ordering is fine, so we stop. So while we first started here, we do what's called a bubble up or sift up. We do a sift up operation. So we started by adding the 15 here. We did the sift up operation. It ended in the way that you see over here at right, with the 15 in this spot. Does that make sense? You just continue until you either reach the root or no swap is needed, which kind of makes sense. So that's how add works. Add where you have to, sift up. Great. How about peek? Well, peek is trivial. All you have to do to peek is say what's at the top. Right? It's always at the root, so it's always awfully easy and awfully fast to do. So no worries there. Now, what about remove? Now, remove gets a little bit interesting because when we remove, we're always removing at the top. So the 10 has to go away, and the only reasonable one to take its place is down here, the last row. We need to make the tree complete. We can't make it incomplete. So we have to take the next thing that's down here, the next one at the bottom, and we have to move it up to the top to take the place of the now removed 10. So it's gone from here and it's been moved up to here. But we're not done. That's just step number one. Then what do we have to do? We do the opposite of what we did with an add, and that is we're going to do a sift down operation. How do we do that? We look at the two children. We pick the smaller of them, right? This is a min heap. We pick the smaller of the two children. We look at the 20 and we look at the 80 and we say, okay, 20 smaller, and is this bigger than the smallest child? If so, swap it. So the 20 moves up and the 65 moves down. Then the 65 is now sitting here. We look at the two children, the 40 and the 60, 40 smaller, so we compare the 65 to the 40. We see that those need to swap, so now the 65 and the 40 have changed places. Now the 65 is sitting here, right? Compare it to the smaller child, that's 50, 50 smaller, so we need to swap the 50 with the 65. So now you see that this organization at right has been accomplished by doing exactly that. The 65 started at the top, it sifted down, it sifted down, it sifted down. We keep doing that until we've hit a leaf node. Okay, until you have no swaps or you hit a leaf node. So that's it. Right? Not too hard. You just have to remember when you add, you put it where you have to add and you sift up. When you remove from the top, you take the next one that's at the end of the heap and move it to the top, and then you sift down by comparing to the smaller of the two children and you move it down until you run out of road. All right, So that makes sense. So how do you, if you have a tree that, let's say you were given a tree, because sometimes you'll run into this, you're given a tree that is not a proper heap, but you need to heapify it. How do you do that? Well, it turns out not to be very hard once you understand all of this stuff. What you have to do is inspect every parent starting with the last. What does it mean to be the last parent? Well, this is the last node, so the last parent is this one. You look at every parent starting at the last one, moving backwards toward the front of the tree, and you do a sift down procedure on every parent. So you do a sift down starting here, then you do a sift down starting here, etc. So we would number them like this. First parent, there's the second one to be acted on, there's the third one, there's the fourth one, then there's the last one. You do a sift down on every single parent, and you keep sifting down until you have not made swaps or leaf, and you go all the way through the heap and inspect every parent. Once you've done that, you have heapified. This will now be a heap. So to practice, pause the video in a second. I've given you a starting set of values. Your job is to heapify. Ready, set, pause. So in our case, if we have taken this and done our proper heapification, we make all sorts of parts of speech out of that, right? If you have heapified properly, this is what you're going to get. Okay? Next, we're going to do remove practice. So go back up to the previous slide, starting there, and let's say that we do a remove. And of course, you know, remove has to always remove from the top. So go back and follow, take that tree and see what happens when you remove. Okay, pause now. What's the answer? Okay. Wait, did we remove? We didn't remove at all. So that's not very well removed. We need to actually do a remove, don't we? There's not another two. So this is obviously not quite right. We've got to do a little bit of a different thing. Okay, so here is a proper answer to that question. I guess I was missing a slide. Sorry about that. The proper answer should be this if I did my remove properly. So we took the 2 off the top, the 8 from down here, right? This used to be an 8. We got rid of that. We moved it up here. Then we did a sift down, so it swapped with the smallest child. Then it swapped with the smallest child. And then once we got to the end, it didn't need to swap here. There wasn't another child. Then we're good. So that's an answer for dealing with remove. So we're going to stop the video there. The next set is going to talk about how we implement a heap, because as you've seen here, we have some mysteries that we've left. How do we move back and forth between children and parents so easily? Do we have to have links that go forward and backward, or how do we have to do this? Well, the surprising answer might be we don't actually implement this with a tree at all. We tend to implement it a very different way, so pick up the next video to talk about how that's typically done. How do you implement a heap? Thanks for watching this one though.